7, let's see.
Yeah, 0.807, which makes sense. It's a positive slope, right? It's going up. How do I make the scatter plot show up? What do I have to, if you have your own calculator and you were with us last time, you should be set up and ready to go. Now watch, if I hit graph right now, nothing shows up. What did I forget to do? Yeah, go to zoom. Well, make sure your stat plot's on, but again, if you have your own calculator, that should be all set up. I forgot to do zoom something. Zoom stat. It's crazy. And once you do that, it should show up. Now, this is not good enough to show me. I've got to see the line of best fit. And if I go back here, I can see my line of best fit. It's about 1140.4x plus 17,600.5. Oh shit, let's see where I remember that. So if I put in here 1140, oh crap, 0.4 is that? Plus 17,650 cents. I like it. Now if I hit graph, there it is, looks good. It looks good. Now just to show you, very often one of the most common mistakes I see is this. Well, that's one thing, is that nothing shows up. But I also see it like it's just a flat line, and that's because people forgot to put their X in there. Well, X dude. So if I put my little X dude back in there, pop, everything's good. Cool. So that's what I need you to come up and show me for Monday's quiz, for example, and for the final exam. There's going to be a problem. You got to show me the line of best fit and scatter plot. I like it. Has everybody able to do this? Anybody have questions right now? Everybody's golden. You know how to do this. You can do it. Quiz coming in. Did you do this on? Okay. Let's see what else we got here, question-wise. So interpret R really means that this is, it's evidence of correlation. There's definitely correlation. It's a decently strong, positive correlation. You guys see how that's a separate question? Of course, that is a physically separate question than what else comes here. What does this R tell us about the line of its fit for this data? I'll take a couple of things here. I'm very open to a few things. So what does it tell us about the line of best fit then? The fact that this R is decently strong, positive correlation. One dinky little thing you can say that's not enough is it's got a positive slope. Ooh, fine. Can somebody say more related to the correlation itself? What does that mean about the line of best fit versus the data points? What's true about it? Since this is a decently strong correlation, the data points, what about them? As a relationship, I like it. The points are relatively close to the line. There it is. It's tight to the line, relatively. You could say that that I trust the line to make predictions. That's something that came up last time. Since it has a correlation, it's decently strong, I could trust it to make predictions like we did last time. So any of those things that you say right here, the data points tied to the line, I trust it for predictions. So for example, the next question says, predict the median income for a state with 23.8% of its population with a bachelor's degree. How do I do that? While I'm looking at this, let me put this down. Or was there? Not there. What was our again? 0.808. How do I do this? Which variable is percentage holding a bachelor's degree? X. So all do, this is the purpose for the existence of formulas, is if I know part of it, I can figure out the other one. So I know the x piece is 23.8. I can figure out the y piece.
So you just leave it 23.8?
Yes, so what's the difference between this problem and the entire rest of algebra? We created this from nothing. And how did I create this, for example? I left everything in percentage form. So what does this equation work with? Percentage form. In general, algebra and math requires the actual number, which is the decimal. Right? I created this damn thing. I can make it do whatever I want to. And then whatever that is. 40.4 times 23.8 plus 17,645. I get 44,741. 25.2. And why did I say compare it with main? What is it about main that makes it comparable to this problem? It's part C. Maine has that percentage. This is a prediction for how much income they should have. And what's their average income? Their median income? 45,503. Pretty damn close to my prediction. Why is my prediction not perfect? Because R ain't 1. Right? R is not 1, so it's not going to be perfect, but it's going to be pretty damn good. If R was like, where'd it go? If R was 0.5, that means it's better than guessing the average, but it would still suck. Right? The estimation would still be not the best. The closer R is to 1 or negative 1, the better the estimation is. Stretch. Okay. Now, you're going to see this question a lot, this kind of question here. We saw that earlier. Do our results mean that if you get more people in a state to earn a bachelor's degree, then the median income will increase? Does it mean that? No, it doesn't mean that at all. Why? Now notice, please dear God, notice this doesn't mean that I'm saying it won't. I can't say it will. I can't say it won't. Some people take that to mean, well, what the shit good is this? There's a relationship, we just haven't done good enough analysis to see what kind of relationship. Are they related to each other directly? Does one cause the other one? I would feel that one causes the other one here, right? This is a pretty straightforward thing, but is that the only variable that affects income? The number of people that have a bachelor's? No, of course not. There's a lot of other variables, and state by state, some variables could have more effect than others. So I can't make a blanket statement, but this is something to analyze further. Yes?
So would you have to say all that for an explanation? Or
Any part of that, right? I need to see some idea that we see correlation, but we don't know what causes that.
So
We don't know if one...
correlation isn't causation?
Sure, but that's not good enough on its own, to be honest. You know, you get a little deeper into the actual problem itself. There's other variables that cause differences in income. I like it, stuff like that. Just get a little deeper beyond catchphrase. I want to show you something where we're on this topic of correlation. Everybody decent with that one? I mean, these are the kind of questions I'm going to ask on that quiz and on the final, related to correlation stuff. I want to show you some silly examples of incorrect correlation. So the number of people who drowned by falling into a pool correlates with the films that Nicolas Cage appeared in, a number of films, I'm guessing. How many films you can see a decent correlation there, right? In fact, they calculated the R value, 0.666. That seems apt somehow. I'm sure you played the devil somewhere. He's played every damn possible character, I think. The per capita cheese consumption correlates with the number of people who died by becoming entangled in their bed sheets. So, if you don't want to die like in that way, then just eat less cheese. I mean, of course, that's stupid, but. So one part of this is, these are really obviously stupid. The same way I'd go, well, if you play more basketball, you become taller, because look,
right? That's equally stupid. But there are things that are nowhere near as obvious that could be mistakes. This feels like hypothesis. There are mistakes we can make because there's always a percentage chance that it's something else or that it's not true or something, right? There's always that chance. And that's why you do follow-up analysis with something that looks like there might be a connection. So I want to see, is there a connection between the number of eggs somebody eats and their general health? Because if there's a certain number you eat, like you need to eat more eggs than we thought, and then you'll be like stupid healthy, or you need to eat no eggs. Or, and of course, how often does that change? The dietary guidelines, how often do they change? Roughly once a month, right? Oh yeah, we said more wine last month. This month, wine's holding pretty steady though, right? Moderation helps you out. Okay, and I don't know. This is called spurious correlations. If you wanted to look, because there's blah, 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 blah. I love it. Oh my God. Letters in the winning word of the spelling bee and number of people killed by venomous spiders. Pretty decent correlation there. They know what they're doing. Oh my God, they're killing people. All right. Spell this word. Don't. Okay. Enough of that. Any questions on that? Since we got that quiz on Monday, anything you want to go over more in depth with correlation stuff? Normally that's a nice section. It's definitely less crazy. Like it's not quite like hypothesis tests. You can sink your teeth into this a little bit better. All right, so we're going to get a little bit into the last bit then, which is chapter 11. And here's the basic idea. So we're going to get a little bit into this, and then we'll probably head out a little bit early. What governs the shape, like how fat or skinny a normal distribution is? So why would one maybe be really fat and another one be really skinny? What's the difference? What governs that? Standard deviation. I love it. So the standard deviation affects the shape of this. And what are these used for? What follows this distribution? Stuff like heights and so forth. And then we've discovered anything can follow this distribution as long as it's sample means where the samples are bigger than 30. Right? We found that out. They all follow this shape. This shape exists. I don't know if I don't think I ever showed you the formula for this shape. There's a formula, I think maybe I did. Just to remind you guys, bless you. It's called a Gaussian distribution, more generally. Gauss is just this guy who did a lot of math stuff, way too much math stuff. He should have let some other people do some of what he did. He's got a freaking unit of magnetic field strength named after him. I'm like, come on, dude. Let somebody else get some of the action there. Here is the formula. Oh, scheisse. Yummy. Every time you drew that curve, you were graphing this function. You didn't even know. Right? You're like, maybe not me, but yeah. Are you guys? Now that is the formula that creates that. If you throw this in your calculator, picking a number for mu and picking a number for sigma, then you would get that shape on your calculator. That is what I'm telling you. That's the function. It's what it looks like. But how did we use it? We didn't ever really, I just showed you that for the first time maybe. And it feels like maybe that was the first time. How did we use this? Well, we have these like raw scores, like heights and grades and shoe sizes and whatever. And what did we do so that they would fall on this? What did I proceed to do to make this become like 0 here? What do I do with those X scores? What would I do? I'm given some X scores, and maybe I'm asked to figure out the probability of something. What do I have to do in the middle? What do I have to do with those X scores before I can look up the probability on that chart? got to make z-scores out of them, right? And there's these, how many formulas for z-score are there? I argue there's basically one, but there are several kind of versions of it, right? Here's very different looking things, right? You guys, semi with me. So this feels like a review, and it sort of is. I'm just trying to make it really clear what we're about to do. So this governs how percentages and means, all these kind of parameters, how they're distributed amongst all the possible samples. That's one good way to look at this. This is the shape that they take on if their sample size is large enough, or if NP and NQ is correct. Are you guys with me? Does this sound familiar? Okay. This shape exists, and these things follow it in certain situations. So here's the problem with this then. The shape itself is governed by sigma, right? Sigma, if it's big, it's fat. If it's small, it's skinny, so forth. What if I want to investigate sigma itself? How is it distributed? That's a problem. I can't use this to figure out how sigma is distributed because this needs to know sigma to know how it's shaped. Do you guys see the problem? Right? How many sigmas are involved in this? One. What if I want several sigmas and I want to see how they look, how they're distributed relative to each other? I can't use the normal curve. I can't. Do you guys see the fundamental issue there? Okay, so what we use instead, if you're a fan of Dragon Ball, you'll love this. There you go. It's the chi-square chart. It's not K-A-I. It's chi squared. And the symbol is this. It's one symbol. It's not something squared. It's the chi-square symbol. You don't square root it. You can't. So don't do that. It's really neat. It's sort of like I took the normal curve and folded it on itself, for example. What's the smallest that a standard deviation could be? What's the smallest that a standard deviation could be? 0. And what would that be? A data list that is made up of what? Same number over and over and over again. How spread out? 7, 7, 7, 7, 7, 7, 7, 7. What's the average distance away from the mean for that? 0. They're all freaking the mean, aren't they? Right? So the smallest it could be is 0. So since this deals with how standard deviations themselves are distributed, it kind of makes sense that it starts at 0. So what sucks for us is we're going to lose, well, to be honest, we're not going to be able to do everything I wish we could. But if you wanted to use this to make confidence intervals for standard deviations, so we are 90% confident that that this interval from 9.8 to 11.3 contains the real standard deviation, right? Same idea as a normal confidence interval, but I'd have to use this. I can't use like negative, positive z-scores anymore. Chi-square starts at 0. Doesn't have a 0 in the middle, it starts at 0. So they're not going to be like symmetric. If one's 2.5, the other one's negative 2.5. Doesn't make any sense because there's no negatives, right? And here's the shape of, to be honest, it's affected by the degrees of freedom, but most of the shapes look something like this. Whoa. We call it the Jabba the Hutt graph. Could just be me, and I don't care because I like it. If you don't know Star Wars, I'm a little sad. I'm sorry. So there is a formula for this shape. We're not going to get into that formula. I don't even know if the book has the formula. But just like there are z-score formulas that follow the shape of a normal curve, there are chi-square formulas that follow the shape of this, right? This curve. So, for example, the really big one is this guy. This is the main one, and this is the one we're probably going to end up not using as much, which is kind of fun. So, for example, recall, z-scores are all about means and how they look. And notice how this thing is governed by the means, right? Whereas this one is all about how standard deviations of samples are distributed. So there's a standard deviation of the population, and there are standard deviations of samples. So if I took a sample of some numbers, and I figure out a sample standard deviation, and I know the population standard deviation, I can then plug that in here and figure out the chi-square score. The same way if I took a sample, got a sample mean, and I knew the population mean, I can then make a z-score out of it. It feels exactly the same. It's kind of cool. This is all brand new, but I'm trying to make the analogy to at least show you that the idea is the same as before. I'm just dealing with standard deviations now, not with means or percentages. So, for example, if we knew sigma was 7, and we find from n equal to 38 things, we find s equal to 11.139. Can you calculate the chi-square score? Take a minute and calculate what chi-square would be for that. It's just plug and chug. What do you guys get for the chi-square? Yeah, so you do 37 times 11.139 squared divided by 7 squared. What are you getting? I'm sorry. 93.61? 9? 691? Okay. All right, sweet. I mean, so it kind of accomplishes the same thing that the z-score formula does. Chi-squared of 0 wouldn't happen very often. That would mean that you picked a sample where all the data points were the same. So if I was doing like picking random students and looking at the distribution of their ages, how spread out their ages are, I'd have to pick all the same ages because the standard deviation, the sample standard deviation would then be 0. That's the only way to get a chi-squared of 0. What did we get? We got a chi-squared of 93. It's up here somewhere. Okay, so, do you guys kind of follow what's happening? So what if somebody else in the same situation, they took a 38 and they got S to be 5.11. What would their chi-square score be? So that'd be 37 over 49, right? Times 5.11 squared. I don't know, it's not like 19, let's see, 21.3, I don't know, they can share.
19.71?
19, I should have stuck with 19. 19.71. So it makes sense it's much, much, much smaller. They got a much smaller standard deviation. I could see where it falls on this. Now, what am I missing, though, to see kind of like where it falls on this? Why is it so easy for us for z-scores? It's 0, and we can see that. But what do we use when we make a z-score, and we want to know what's the probability of getting a sample with that? What am I missing to be able to do that? I'm missing a chart. Well, I got that. Oh, shit. Another chart. I live off of your groans. This is Stanley.
Oh, good y'all.
Now, people that created this chart, not the chi-square. People that created chi-square are awesome people. People that created this chart are sadistic AF. Because compared to z-score chart, when I look up a z-score, it tells me the area to the left, area to the right. You guys see what I'm saying? So this gives me the area to the right of some value, some critical value. Right? But let me see. I don't want to. Yeah. Okay. So the hard part for us. Now I want to. This is not how we're going to use this, but just to relate it to what we've done. This makes it difficult because I want you to realize the same way that the t-score chart to be as informative as the z-score chart, I would need a separate chart as big as the z-score chart for every degree of freedom. Same thing happens here. So I'm going to desperately hope some of you guys get what I'm about to say about what we just did, those two calculations we made. Degrees of freedom for us for that situation was 37. Is 37 on there? No, shit. Oh well. It's too bad, bro. We'll use 40 just to be close. If I look on here, we got 93.691. That's off the chart on this side, right? So that's like way off the chart. What area is to the right of our, what do you call it? What area is to the right of our chi-square is going to be very little. So it's just, it would be way the shit up here. Way up here. Okay. What about 19.71? So for almost 40 degrees of freedom, 19, look at this is too good of it. It's almost exactly this. So what area would be to the right of that score? 99.5%. So it would be like right here. That would be the 19.71. And the 93 would be way the shit up here with approximately 0% in front of it. You guys start to see how I can't feel out where things are placed without the chart. The z-scores are a little bit easier because they're symmetric around 0 and so forth, and it's really easy to talk about them. This one changes. Every degree of freedom has its own kind of way to distribute. That's why this is a little bit harder to look at. Now, let's rein it back in to the kind of problem we're going to do. I think, yeah, I'm just going to stick with what I've got on the homework sheet. I was thinking about changing to do this, but I don't think I will. There's this really kind of kick-ass just like the z-score formula has multiple versions of it, based on if you're looking at percentages or you're looking at sample means or whatever. There are multiple versions of the chi-square formula also. One of them is remarkably unexpected, which is a really funny word to use. And it deals with something called, and I'm not making this up, it's called the goodness of fit. Fest. Right, this has nothing to do with physical health. It's not trying to see if you're ready to become a Navy SEAL or something. This means the other definition of fit, which is how well does something fit our expectations. So, for example, if I believe that, what was on this? Oh yeah, I didn't bring it with me. Shoot, that's all right. If I think that M&Ms are uniformly distributed, right? There's the same number in each bag. Are you with me so far? So uniformly distributed. So let's say I have, what's the, oh shit. What colors are there nowadays? Red, yellow, brown, blue, I think is the new one, right? Green. What's that? M&Ms. Yes. Yeah, I think blue's relatively, remember, I'm old as shit, so new to me could be like in the last 20 years. Orange. So if I think that these are uniformly distributed, is everybody with me? That's kind of like the claim. Now, please, dear God, the minute I say that word, people are like, bless you, bless you. They're not bless you, but they are we going to do hypothesis test again? No. No, we're not. I could, but we're not going to. But my claim is that they're uniformly distributed. So expected amounts of each can be figured out then, right? Expected amounts of each. So if I got enough bags to have, let's say 600 M&Ms, then how many of each color would I expect to have? 100. Please let that be easy. When it's uniformly distributed is the expectation. I just divide the number of categories. Let me write that down. This is the categories. So what's the number of categories here? I'm making a big deal of this because it's important. Number of categories in this case is 6. So how many do I expect in each category? 600 divided by 6. I expect 100. Right? Basic shit. Okay, just human level of capacity of computation numbers. So this will be, I would expect 100 in each. Now if I crack them open and get 600 of them and actually count how many of each color I get, that would be the observed amount. Spell correctly. There you go, buddy. At least nobody's going to die from venomous spiders because of me. I then just put down how many observed. So let's say I see 80 red, and I see 110 yellow, and I see 100 brown, and I see 110 blue. I see 90 green, which means I was sort of keeping track, and then I forgot. I think it means I need 110 orange. Is that true? Let's see. 220, 300, 400, 500, 600. Yeah, cool. So there's expected, that's based on the claim. The claim will not always be that they're uniform. The claim could be, I think 20% of them are going to be red, and 30% are going to be yellow, and blah, 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 blah. Right? In which case you do 20% of 600 to see what goes here, 30% of 600 to see what goes there, so forth. So you use the claim to see what you expect to happen, and then I just got to tell you, well, here's what the hell happened. All right, I like it. So what we're working towards, so that's the setup. So obviously what's going to come into play here? What would mean that I was exactly right is if the difference in these two came out to be the difference between these two came out to be 0. If these were the same, then the difference would be 0. So what I want to measure then is how far away from 0 difference is it? And there's going to be a certain thing that tells me how far away is far away enough. Oh boy, that sounds a lot like hypothesis test. I love it. So remember, a chi-square looks like this. Wow. So this would mean, if I got here, that would mean my expectation was exactly what I observed. Right? Which never ever happens. And anything that's different, if these are different at all, it's going to start to go this way. Right? Now I haven't written what the formula is yet. And in fact, let me see if I even remember. It's been forever. Oh shit. Let's hope that's true. Let's all find out together. So if I remember correctly, that's what that sucker is. That's a big if. Blah, 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 blah. Oh my God. Okay, good. So notice there's a big old summation symbol here, right? So I need to do observed minus expected, and then I got to square that, and then I got to divide by expected. So it sounds like some lists are going to be happening. Do you guys get a feel for how this is? Let's do this one problem, then we'll head out early. Let me write this over here. Poor little dude. So there's one chi-square score, one chi-square possibility, and here's another one. So, what's my observed minus expected here? And to be honest, the negatives don't matter worth shit because the next thing you're going to do is square it, right? But let's just be totally, let's be 10, 0, 10, negative 10, and 10. What do you think these would normally add up to be? 0, makes sense, right? Negative 20, bam, bam, they all cancel each other, right? So so we square them for the same kind of reason we squared standard deviation stuff, because they would always come out to be 0 and tell us shit, right? So now we square it, observed minus expected squared, and we get 400, 100, 0, 100, 100, 100. And then we get 5, 6, 7, 800. But that doesn't matter. Because what's the last thing I need to do? And this is the thing. Notice how that summation symbol is huge? This whole thing is in here. So what do I need a list of? I need a list of those. So the last thing I got to do is take those and divide by the expected. Thank God the expected is all 100. That's too beautiful to believe. I just got to move the decimal back a couple times. So this is observed minus expected squared divided by expected. That'll be 410111. Five, 6, 7, 8. So the sum, the chi-square, is the sum of, gather, little tiny thing, which comes out to be, in this case, 8. Do you see how that's a measure, the relative measure of the difference between these two? All right, we took a difference and we divided by the expected. Get a relative measure how different they are. Because a 0 difference would mean, okay, I was exactly right. I want to see how far away from 0 I got. I got 8 away. Can somebody help me out? Here's the last piece of this. For us, degrees of freedom will be number of categories minus 1. So they use the letter K for number of categories, just to spell categories wrong. So in this case, how many categories were there? 6. So 6 minus 1 is 5. And if I use alpha equal to 0.05, which is the standard alpha, and here's the idea. So the idea is I need to be far enough away. I need to be way the shit out here to show evidence that they really are different. So if I get here, that's evidence that they're different, that it's not what I expected. If I get back here, that's not evidence that they're different. I didn't prove that they're not the same. So I need to know what that is. So this would be 0.05. So degrees of freedom was 5. Alpha is 0.05. Can you guys see what the score is? What's my critical score? What's my rejection region kind of score thing? So degrees of freedom 5. Alpha is 0.05. 11.071. And we got what? We got 8. Did we get far enough away to show evidence that they're different? No. So I can't say that I'm wrong. I can't say that they are not uniform, right? I can't say that that's wrong. I didn't find enough evidence to show that they're not uniformly distributed. You guys see that? And some people would go, but Jeff, look, the numbers are different. But again, this is a sample. If I took a larger sample, maybe that would become 100 and maybe so forth, right? Or not 100, but whatever the number would be for the bigger sample. Okay, maybe. All right. To be really honest, that's further than I thought I would make it today. And you're all like, yeah, just keep barfing stuff at us. It's great. Next time I'll have, remarkably enough, a little worksheet on this that we'll do after the quiz. So quiz on correlation stuff on Monday. Everybody got a practice final too, right? Okay. Yeah, please don't forget your whatever you gave me.